So we now have an understanding of how we can measure circulation, not just on an aggregate total basis using an integral on a closed loop, but also measure it infinitesimally, like the circulation density, the scalar curl of a vector field at a single point is telling us how that vector field is circulating right at a single point, in a sense, how it's spinning a tiny little sailboat that we might place into the flow at that point. And so what we want to do is kind of bring all of these threads, pull all these threads from today together into figuring out a way that we can compute the circulation of a vector field without needing to do the circulation as a line integral, but to make use of this circulation density, the scalar curl function. Because the scalar curl function can tell me the circulation at each individual little point in the xy plane. Can I do something with that scalar curl function to add it up together to give me the actual circulation around a large path? So what does the total circulation have to do with this circulation density? And that relationship comes in the form of our second big theorem of the day called Green's theorem. So to get us a preview into what Green's theorem is, here is a vector field off to the side over here. And if I were to wonder what is the circulation of this vector field on, let's say, a circle centered at the origin, right? At least for this vector field, it looks like there are some places where that circulation is going to have a positive quality to it, right? If I'm going counterclockwise around this circle, then this little green area over here is a place where the line integral is going to have a positive contribution because we're going roughly parallel to the vector field. But then in these other places where we have the yellow shading, we're traveling counterclockwise means that we are going against the vector field, and so we're getting a negative contribution. And so the total contribution is going to be negative. So the total circulation around this circle is a negative number. It's negative 29.3 or so. That's this circulation number that's being reported by our vector field analyzer tool. But on the other hand, what's interesting for this particular vector field is that if instead of choosing a circle centered at the origin, I had chosen a circle centered in a different spot, my circulation ends up being the same amount, no matter where I place my circle around the xy plane. The circulation is all negative 29.3, which seems too surprising to be a coincidence, mathematically speaking. The other thing that we notice is that if I change the size of my circle, then my circulation does change. But there's something else that's not changing in the process. What's not changing is the relationship between my circulation. Let's say I find a circle that has a circulation that's about equal to 30 or so. My circulation is about equal to 30, but the area of this disk, so the area of the circle that's being bounded by my curve, is exactly half and negative sign as much as the circulation. So there is a common ratio for any circle that I can draw in between the circulation around that circle and the area of the disk that's being bounded by that circle. That it seems like the circulation is just negative 2 times the area, no matter how large or how small my circle is. And indeed, even if instead of a circle I had a rectangle, and regardless of where I place that rectangle, again, we have that same negative 2 to 1 ratio between the circulation and the area of my rectangle, no matter how big my rectangle is and no matter where I place my rectangle. So what is explaining this coincidence is what we're going to forge ahead towards next and figure out how Green's theorem is going to let us evaluate a circulation integral, not by integrating the dot product of the vector field along the boundary of my region, but by doing a double integral of a quantity on the interior of my region. And so this is going to bring us back into a place where our multiple integral techniques are going to be useful once again. So when you found the circulation of this vector field around a circle of radius 2, you found out that its value was something like 14.9 or whatever. And that most importantly, that ended up being 3 times the area of this circle. And so your speculation was that, well, if it's true that, at least in this case, that the scalar curl is the ratio in between the circulation and the area, that maybe this is something that's generally true for this particular vector field, that the circulation is just equal to the scalar curl times the area. And if that's the case, then because we can compute the area as a double integral of the integrand 1 over whatever region that my closed curve is bounding, then perhaps we can compute the circulation as the integral of the scalar curl with respect to area. And so the prediction that you made, and I just realized I didn't put this in my camera until just now. So there it is. The prediction that you made was that, again, since the scalar curl appears to be the ratio, in this case 3, between the circulation and the area, that the circulation of this example was 3 times as much as the area of the circle that it was bounding. That in general, maybe it's true that the circulation is the double integral of the scalar curl. And that right there is exactly Green's theorem. All right, so Green's theorem is the statement that for any simple closed curve, so our closed curve should not be allowed to intersect itself as we go along. The only place it should intersect itself is back at our starting point. So we can't make like a figure 8, for example, but we can do any kind of triangle or square or polygon or circle or whatever that we would like to do. That the circulation around that loop is the double integral of the scalar curl. Notice also that we needed to agree on an orientation. We needed to agree on a counterclockwise orientation in order to make this work, and that's also the orientation that the vector field analyzer is assuming. Whenever you draw a box or a circle in that tool, it assumes counterclockwise orientation. Because remember, counterclockwise rotation was when scalar curl was positive, when we discovered scalar curl in the previous section. So that's why we want counterclockwise orientation to make that coherent. Another way to say it is that if I am walking in the direction of my parameterized curve, then the area inside the curve, so the disk in this example inside the curve, should be on my left as I walk around, right? So if I'm a little person walking around the edge of this circle, then on my left side should be the region that we're going to integrate over, and on my right side is open space, right? So that's the sort of convention that we use to determine the counterclockwise orientation for the purposes of Green's theorem. So what we're going to look at next is just a quick summary that pulls together everything that we've learned so far today, and then we'll do one example of where you'll get a chance to apply Green's theorem to evaluate the circulation where maybe the scalar curl is not a constant in those cases.